Yeah, we can hear you.
All right. So the first exam for the course will cover chapters 2 and 3. Exam problems, very similar to the homework. Oh, did I start the recording? I did, yeah. Will be very similar to the homework problems. So the exam will do like an hour and a half. Will take place during class time, and we'll talk more about that, how we're going to do it later. 6:30 to 8, and then from 8 to 8:45, we move on to new material. Actually, maybe that's a little bit much. 8:30 to, I don't know, 7:50, I guess. And then from 8 to 8:45, we'll move on to new material. All right, and so, I mean, it's still pretty early on into it. I think, so next Monday, let's tentatively schedule for, let me think. So today, this Monday, or Wednesday, these Wednesday of next week. So here's Wednesday the 19th, so Wednesday the 26th. So tentatively, we will schedule the exam for Wednesday at not 10, 5/26. Okay. So it'll either be Wednesday 5/26 or the Monday after that. I don't think. I think we'll be able to get to it on that Wednesday. Right. So today we're going to go over sections 2.5, 2.6, and 2.7. So I hope we all watched the video lectures. And now we'll work on the discussion problems. So the first one in section 2.5 is number 243. Wait a minute. Yeah, 243. Somewhere. So section 2.5, 243. Here. All right, so for the following exercises, points P and Q are given, and let L be the line that passes through P and Q, and find the vector equation of the line. And part B is the more important one, find the parametric equations of the line. the symmetric equations of the line and the parametric equation from the line for the line segment from P to Q. All right, so we've got this section 2.5. All right, so in 3D, lines become a little something different, more complicated than what they were in 2 dimensions. So we've got -3, 5, 9, and then 4, -7, 2. And this is the point P, this is the point Q, and then this vector between them with P at the tail and Q at the head, that's PQ. So we'll just call it V. And V is what's known as the slope vector, or the direction for the line through PQ. Okay, and again, just sort of quick review of what we talked about in the lecture. So here's the line through PQ. So, or the line containing the point P in the vector V. So if this is the vector through P, so the vector in standard position, so we'll just call that P, and we'll call that V. All right, then any other point on the line is just P plus TV. All right, so like over here, this point right there, call it R, is P plus T times V for some T. All right, here's T times V right there. And so there's P plus T times V. And if you want the points over here, using negative values for T. All right, so that's the vector equation of the line. And then that gives you the other equations as well. So in this case here, we have that V is equal to head minus tail. So that is 4 plus 3 is 7, minus 7 minus 5 is minus 12, and 2 minus 9 is minus 7. Okay? And therefore, and we'll write R is equal to X, Y, Z. So we'll write out the vectors explicitly. So all points on the line are of the form X, Y, Z. All points X, Y, Z on the line are of the form X, Y, Z is equal to, so P, and you could use Q, or you can use P, whichever one you want, -3, 5, 9, plus T times V, which was 7, minus 12, minus 7. Okay, so that's the vector form of the line. Vector equation of the line. The parametric equations, you just write x, y, and z separately. So x is equal to -3 plus 7t. Y is equal to 5 minus 12t. Z is equal to is 9 minus 7t. So those are the parametric equations. That's the most useful form. They also have this thing called the symmetric equation of the line, and I'm just going to leave it out because I don't like it. I don't know why it's made why folks make a big deal out of it. But well, the way you normally express it is in this parametric form. And what do you notice about the parametric form? Where's the slope vector? It's right here. It's 7 minus 12 minus 7. The slope vector are just the coefficients of the t, right? Just like they are in 2 dimensions, right? The slope vector is the coefficient of x, right? There was y is equal to mx plus b, but you just get the slope as one number, just the m. Here, you can't get that, so you have to have these 3 parametric equations. Now, how do you get the line segment between P and Q? What values of T are used for the line segment between P and Q? If you just want these points in here. If you just want these points here, what values of T would you use?
Would it? Never mind, I don't know.
Nobody? Right, I mean, like in the picture I drew here, the value of T used is greater than 1, right? And if you want points over here, right, these would be values of T that are negative.
So it'd be 0 through 1?
0 to 1, exactly, yeah. All right, for the line segment, from P to Q, just restrict. And, we'll use this idea later. Zero less than or equal to T less than or equal to 1. For T equal to 0, you get P. For T equal to 1, you get Q. And then for T's between 0 and 1, you get all the points in between. All right, so that's how you deal with lines in 3 dimensions, is with these parametric equations. Next, 251.
I had a quick question.
Sure.
About that one. For the parametric equations, the base part that's not the slope, do you have to use the head part of the line for that, or can you use the tail?
I use the tail in that one. The head of P. You can use any point on the line. Any point in the line that you want, so I just picked P. You could have used Q if you want. It's fine. Right?
All right.
Mm-hmm. So often you'll have an equation for a line or an equation for the plane will require as one of the ingredients a point on the line or a point on the plane, and you may have several points, in which case you can just pick whichever one is your favorite. It won't matter which one you choose. It gives you a different set of equations, but it's the same line. Alrighty. 251. So here the line L is given. Find point P that belongs to the line in the direction vector V of the line. Express V in component form. Find the distance from the origin to line L. Okay, nice. So 251. See, they give us these parametric equations. So x, y, z. So x is minus 1 minus t, and 2. Right, so the slope vector of the line is what? Or direction vector, they're calling it. What is it going to be? Well, it's the coefficients of t. All right, so here it's minus 1, 0. There's no t's there. Right, so it's minus 1, 0. And then they're asking Find the distance of the line L to the origin. So this line is L, and find its distance from the origin. So what does that mean exactly? Right, it's the sort of closest point, right? The closest point to the line from the origin. Okay. Well, we need 1 point on the line to start with. Right, we need 1 point on the line to begin. So this uses the techniques from section.
Yeah, your screen disappeared.
Oh, did it? So we need 1 point on the line to get started. Okay, so somebody pick a point here. Give me 1 point on that line. Oh wait, do I have the right equations? What number was this? 251.
I thought they give you a point, don't
Oh
they?
yeah, I got the wrong equations here. What are they? 1 plus
I don't know.
3 plus t, 5 plus 4t. What was I looking at? 1 plus t, 3 plus t, 5 plus 4t. So 1 plus t, 3 plus t, 5 plus 4t. So the slope vector is 1, 1, 4. All right, now I need some point on the line to get started. So somebody have a point on the line I might use?
I use the point 135.
Sure, 1, 3, 5. 1, 3, 5. Okay, so right here is going to be the vector pointing back to the origin, minus 1, minus 3, minus 5. Right? And here we have this slope vector. So let's redraw this. So here's the line, 1, 3, 5. Here's the origin, 0, 0, 0. So here's the vector, minus 1, minus 3, minus 5. And here's the slope vector, 1, 1, 4. So now we're looking for this here. Right? And say this angle here is theta. And we'll call this vector v. Right? How do I get this length here? Trigonometrically. So this is the distance we're looking for. Right, that's the distance we're looking for. So trigonometrically, how do we get that distance? Right, just using basic trigonometry. Because the shortest distance of the origin to the line or the point to the line is going to be this perpendicular distance. So how do I get that?
Isn't it v sine theta?
Yeah, length of v sine theta. Okay, and then we also have this slope vector here. What should we call it? We'll call it u. Okay, so this is equal to length of u, length of v, sine of theta, over the length of u, sort of uncanceling the u. Right, and then what's this? What's length u, length v, sine theta? In terms of these products we've been talking about. Length of the cross product. right? So we don't actually have to do any trigonometry here. We have all the coordinates we need, and it's all just kind of buried in the trigonometry. Or sorry, it's all buried in the cross product. But the trigonometry is buried in the cross product. That's what I'm trying to say. All right, so here's U cross V. So I, J, K, 1, 1, 4, minus 1, minus 3, minus 5. So this cross product is, so in the I component, we got 1, 4, minus 3, minus 5, that 2 by 2 determinant. And in the J, we got 1, 4, minus 1, minus 5. That 2 by 2 determinant negated. And then in the K coordinate, 1, 1, minus 1, minus 3. So this is equal to, so minus 5 plus 12, so that's 7. Minus 5 plus 4, it's minus 1. And then, oops, minus 5 plus 4 is minus 1, then negate it, positive 1. And then, minus 3 plus 1 is minus 2. So 7, 1, minus 2. So that's U cross V. So the length of U cross V is 49 plus 1 plus 4. So that's square root 54. Alright, so that's 54 is 9 times 6. So 3 square root 6. So the distance over here is 3 square root 6 over length of U. Length of U is square root 16, 17, 18. Alright, so 3 root 6 over square root 18. So that's 3 root 6 over 3 root 2. So just square root of 3. Okay. So that's more of a question from 5.4. The only, or 2.4, the only bit we used here is that we got the slope vector right off of these equations here. The slope vector for that line is 1, 1, 4. And a point on that line is you know, whatever you can stick into these equations, just t equal to 0. So we just got 1, 3, 5. Okay, so we got this vector, minus 1, minus 3, minus 5, the 1, 1, 4. And then this distance is length v sine theta, and then we put that u in there, and then it turns it into a cross product problem. So, you know, we calculated that area, or sorry, that distance, without actually doing any trigonometry. Well, without calculating any sines or cosines. I mean. 255. We certainly did trigonometry. We thought about it. All right, 255. So you have these two lines, L1 and L2. Verify if the lines are parallel. And if the lines are parallel, find the distance between them. So in 255, you've got L1 is got these equations. 1 plus t, y equals t, z equals 2 plus t. So that is line 1. And then you've got line 2. X is equal to 3 plus t. Y is equal to 1 plus t. And z is equal to 3 plus t. So the slope here, right, is the coefficients of the t. It's just 1, 1, 1. And the slope here, 1, 1, 1. So the same slope vector. So the lines are parallel. Right? Because, slope 1 is equal to k times slope 2. So, you've got slope vector 1 and slope vector 2, and they're multiples of each other. I mean, they're actually the same, but, fine, the multiple is 1. Okay, so that means the lines are parallel. Okay, so also, by the way, when lines are not parallel in 3 dimensions, when lines are not parallel in 2 dimensions, they have to intersect, right? Here, no. I mean, 2 lines that aren't parallel, I mean, they don't have to intersect, right? I mean, one can live in one plane and another in another plane, and the planes are parallel, but the lines are not. You can have this kind of thing, right? I mean, I have a line down there in the XY plane, and then I got a line up here in the plane like z equal to 3 or something. Let me see. I've got parallel planes like that, parallel to the XY plane. I have a line in here, and I got a line in here. Those lines aren't parallel, nor are they going to intersect. So, whereas non-parallel lines have to intersect in 2D, 3D is a lot bigger, and you just can't make it happen. I mean, it can happen, but it doesn't have to. All right, so find the distance of line 1 to line 2. So, how would we do that? All right, well, we've got L1 here, and we'll take a point on the line. So a point on the line will be 1, 0, 2. Right, 1, 0, 2. And then I've got the other line. I need a point on there, 3, 1, 3. And I've got that slope vector, 1, 1, 1. So we'll call that U. And then I've got this vector from here to here, right, which is, stop please. This vector here, which is 1 minus 3 is minus 2, 0 minus 1 is minus 1, 2 minus 3 is minus 1. Alright, so this distance right here, same as before. Right, that perpendicular distance. And so this is line 1, line 2. So that distance is the length of U cross V over the length of U. Right, so we got to do that cross product, and then plug it into here. So U cross V is equal to I J K 1, 1, 1 minus 2 minus 1 minus 3. So that cross product is minus 3 plus 1 is minus 2. The J is minus 3 plus 2 is minus 1, and then negate it. And the K is minus 1 plus 2 is 1. So negative 2, 1, 1 is U cross V. Did I do that right?
For the V vector,
that's a minus 1.
-1.
Yeah, minus 1. Okay, let's fix that now. So this is minus 1 plus 1, that's 0. The J is So that's minus 1 plus 2 is positive 1, and then that becomes a negative 1. And then the k is minus 1 plus 2 is 1. So 0, 1, negative 1, 1. So the length of u cross v, also the distance, is equal to the length of u cross v. So square root of 2 over the length of u, square root of 3. So square root of 2/3. Okay, is the distance. All right, so when lines are parallel, you can do that calculation and it makes sense. Right, it gives you the distance from line 1 to line 2. And it doesn't matter which points you pick, right? I can take this, I mean, when lines are parallel, I can slide this, this vector and this vector, I can just slide it along L1 and L2, right? And that distance D never changes, right? So this vector and this vector, you can just slide it along here, and that distance D never changes. Or you could have different vectors, right? Maybe the other vector is over here or whatnot, but that distance D is the same, right? The perpendicular line segment going between those two lines, it's always the same length because they're parallel.
I think the book did the cross of the point you did and then the slope vector. Because their answer is a little bit different.
That's the way what I did. I took this vector.
Oh, yeah.
Vector. That must be what they did. Did they do something else?
I don't know. Their answer was 2 multiplied root 2 over root 3, I think.
What number is this? 255? I can't imagine.
Unless I'm wrong. I don't know.
I can't imagine.
No, I'm wrong. I'm sorry. Never mind.
Okay. 255 parallel, yeah, root 2 over root 3.
My bad. I misread it.
Sorry. Happens. All right. 255, 256, 257. I imagine those are all the same problem. 256, same thing. So we have L1 So what do we have here? X is 2, Y is 1, Z equals T, so that guy is parallel to the Z axis. And L2, I should write an equal there, just like that. X equals 1, Y equals 1, Z equals 2 minus 3T. Here the slope vector, so slope 1 is, so it's just the coefficients of the t, 0, 0, 1, and then slope 2 is 0, 0, minus 3. Parallel or not parallel? Are the slope vectors multiples of each other?
Yes.
Yeah. So slope 2 is equal to minus 3 times slope 1. All right, so parallel. All right, so same thing as before. We'll take the cross product. So we'll set up the same calculation as before. So here's L2, say. And we'll get a point on that line. 1, 1, 2. And here's L1, parallel to that. Get a point there, 2, 1, 0. So we've got this, I shouldn't make them like that, let's put it here. So we've got this vector v in between them. which is in general not perpendicular to the two lines. So that's 1, 0, 0, minus 2, minus 2. And then we've got the 0, 0. Now, the slope of line 2 is 0, 0, negative 3, but I could just use 0, 0, 1. Okay, because they're parallel, right? As long as the slopes are constant multiples of each other, you can always just use whatever slope you want, right? I mean, if it simplifies matters, which, it probably does. All right, so we have that u and v, and then the d is right here. So the d is length u cross v over length u. So let's write this a little differently this time. So a little slightly different approach to cross product. So here the what is this v? Well, what is the u? U is just k. K cross, and what is v? I minus 2k. Why I'm writing in red, I don't know. All over the length of u. All right, length of u. Well, the length of u is just 1. All right, it's a unit vector. Okay, so remember how cross products work just on I, j, and k, right? There's this triangle, I, clockwise, j, or the other way if you want, clockwise, k, clockwise, I. Right, and, I cross j is k. J cross k is I. And k cross I is j. And then the other way around negates. When you do the cross product the other way around, it negates it. So if you're going clockwise, taking the cross product clockwise, you get I cross j is k. If you're going the other way, k cross j is minus I. All right, so this is minus k cross j minus I cross k. So I'm going to do the calculation this way. And then, you have distribution over addition. So this is k cross I, and I'll skip the hats for now, minus 2k cross k over 1. Right? What's k cross I? Right, k cross I is j. K cross k is what? Because k is, of course, parallel to itself. Right? The length of k cross k is sine of 0, right, which is 0 over 1. Whoops, the length of that. So it's just the length of j over 1, so it's all just 1. So that distance is 1. All right? So a slightly different approach to cross product. Not that you should do that approach. But, just wanted to show it to you. And this is how cross product moves into 4 dimensions, by the way. So you take 4-dimensional vectors. So 3-dimensional vectors are of the form AI plus BJ in IJK form plus CK, like that. And then to pop it into 4 dimensions, you just put D. So that's a 4-dimensional vector. And the D, the vector that goes, D is just a number, it's just a scalar. There's no other directional vector that goes with it. And then when you want to multiply two of these guys together, you just use this distribution property and this cross product mnemonic here for I, J, and K. And then I cross 1 is just I, of course. Right. So, yeah, that's how cross product goes into 4 dimensions. And that gets used a lot when studying quantum mechanics. Well, not a lot, but when you're studying quantum bits or quantum bits of information, brackets they're called. So it's pretty cool, and there's lots of nice geometry that goes along with these 4-dimensional objects. And it's only in 3 and 4 dimensions. Only in 3 and 4 dimensions. This special cross product geometry. Only in 3 to 4 dimensions. Doesn't extend to higher dimensions. There's similar algebraic structures in 8 dimensions and similar in 16 dimensions, although they're not as nice as this. So it's just beautiful stuff. What can I tell you? 257. Show that the line passing through PQ is perpendicular to the lines with this equation here. So we've got the line through PQ. So here's P, 3, 1, 0. Here's Q, 1, 4, minus 3. So this vector V here is so 1 minus 3 minus 2, 4 minus 1 is 3 minus 3 minus 0. And then the other line L has these parametric equations. X equals 3t, y equals 3 plus 8t, z equals minus 7 plus 6t. So its slope u is 3, 8, 6. Now, why would L and the line through PQ be perpendicular? What would make them perpendicular?
Is it at the dot product 0?
Right, if their slopes are perpendicular, right? So the lines are perpendicular. If and only if their slope vectors are. All right, so here we have minus 2, 3, minus 3, dot 3, 8, 6 is equal to minus 6 plus 24 minus 18, which is 0. So they are perpendicular. Okay. Yeah. All right, that was 257. $261, $264. Determine whether the lines are equal, parallel but not equal, skew, or intersecting. All right, so some nice problems here. Skew would just mean not parallel. Not parallel but not intersecting. So I mean, let's talk about this. So we got what, 261, 264. let's do all three of these. Maybe we'll get some interesting. I don't know. Let's take a look. So L1. Oh, what did they give you? Oh, they gave you the symmetric equation. So I mean, it's just annoying. So the symmetric equation is the line. So I'll show you what it means. So you have L1. You get this x. So first of all, it's not an equation because it's got three parts to it. Equals minus z. And then L2 is x minus 2 minus y z over 2. X minus 2 minus y. Like that. Okay, so essentially these are all solved for t. Right? So you can set all of that equal to t. Right, so this says x equals t, y equals t plus 1, and then z equals negative t. So that's how you go from the symmetric equations of the line to the parametric equations for the line. All of these are essentially just t. So or you know, in the parametric equations, you can solve for t. So you solve for t in terms of x, y, and z, and since they're all equal to t, they're all equal to each other. But what's the point? I don't understand why that's liked. So here, x is 2 plus t, y equals minus t, and z equals 2t. So that's L1, that's L2. So the slope here, right, so I mean you can't read the slope off of it. Right, the slope here is 1, negative 1, 2. Right, so slope 2, 1, negative 1, 2. You can't read it off of that. Slope 1 is equal to 1, 1 minus 1. All right. Are those multiples of each other, those vectors? Can I multiply s by some scalar k to get t, or to get s2? Well, obviously not, right? I mean, s1 is not equal to t times s2 for any t. Right? Because, I mean, if s1 was equal to t times s2, because that's 1 and that's 1, that t has to be 1. Right? But if t is 1, well, 1 times 1 is not negative 1, and 1 times negative 1 is not 2. So it just doesn't happen here. So these are not parallel. So now the question is, are they skew? In other words, they don't intersect, or do they intersect? Okay? Do they intersect or not? So not parallel, but do they intersect? Or not? Okay, if two lines intersect, right, they'd have some intersection point. So this intersection point is going to be equal to, R is going to be equal to P times slope 1 plus, I don't know, V1, I guess we'll call it. It's also going to be Q times slope 2 plus V2. Right, so there's going to be some scalar multiplied by the slope vector, such that when you look at this vector form, right, these 2 points are going to be the same. So the tricky bit is that you can't use the same scalar when you're trying to solve here. Right, so you need 2 different scalars, and then you set things equal to each other. Okay, so let P and Q be scalars, right? So we need that P, right, X is equal to P is equal to 2 plus Q. So use P for this line, Q for that line as a scalar. Y is equal to P plus 1 minus Q. And Z is equal to minus P 2Q. All right, well, this one, right, these two equations, these tell you what? P minus Q is equal to 2, and this one says P plus Q equals 1. Or let's not do it that way, okay? So take these two equations, right? This one says P is equal to 2 plus Q. P is equal to 2 plus Q. So I'm going to put 2 plus Q in here. All right, so 2 plus Q plus 1 is minus Q. All right, so what does that give me? That gives me Q plus 3 is minus Q. So 2Q is minus 3. So Q is minus 3 halves. So Q is minus 3 halves. And then P is equal to 2 plus Q. 2 minus 3 halves. So that's 4 halves minus 3 halves is 1 half. So I got P equal to 1 half, Q equal to minus 3 halves. Now plug them into here. Does it give you an answer? Right, I've got two unknowns. I've got unknown P and I've got unknown Q. So for two unknowns, how many equations do I need to solve uniquely? 2. Right, 2 unknowns and 2 equations will typically give me a unique solution for the 2 unknowns. But what do I have? I got 3 equations and 2 unknowns. So that third equation is redundant. Either it's redundant or it's going to tell me there's no solution. And here, in this case, what happens? But, right, minus P is equal to minus 1 half. And then 2Q is equal to minus 3. Not equal. Right. Right, this one says Z is equal to that, and this one says Z is equal to that, and that's a contradiction. Right, so no intersection point. The lines are skew. Okay, so when you want to find the intersection point, if there is one, of two lines, you pick two different scalars, P and Q, S and T, A and B, whatever you like. Use one scalar for one line and one scalar for the other line, and set the parametric equations equal to each other. Set the parametric equations equal to each other. Okay, and then the first two parametric equations should give you a unique solution for those two unknowns. It might not. It might give you a not unique solution, in which case you should be able to get a solution for the Z. But here they gave me a unique solution, and it doesn't work for Z. So two unknowns, all I need is two equations. The third equation is either going to be redundant or is going to give me a contradiction. 256. So yeah, 250. No, it's 261, 264. Same thing, right? We've got these lines again. So 3x 3x equals y plus 1 equals 2z. And L2 is 6 plus 2t, 17 plus 6t, and then z is 9 plus 3t. So that's L2. L1, again, these are all equal to t. X is equal to 1/3 t. Y is equal to minus 1 plus t. Z is equal to 1/2 t. So that's L1. Right, so here the slope is equal to 1/3, 1, 1/2. And here the slope is equal to 2, 6, 3. Are these multiples of each other?
Yes.
Yeah. S2 is 6 times S1. Right, so L1 and L2 are parallel. Oh, hold on a second. Are parallel? Are they the same? Are they the same? All right, so are parallel. L1 and L2 are parallel. Are they the same? They have the same slope vector, but I mean, are they actually the same line? Well, how would you know that? How could it find that out?
If they have a common point in their parallel.
Yeah, I mean, yeah, all you got to do is find one common. They are parallel, and all you got to do is find one common point, right? To find out, so let's ask, is the point 0, -1, 0? So the point 0, -1, 0 is on L1. Is it also on L2? So let's check it out. So here's those equations for L2. And let's just plug in x, y, z, 0, -1, 0, and ask, do we get a solution? Do we get a solution? So 0 -1, 0. So this tells us that t is equal to what? T is equal to, so -6 over 2 is -3. This one tells us -18 divided by 6, t is equal to -3. This one tells us t is equal to -3. Right? So yes, 0 -1, 0 is also on L1. So you have two parallel lines which have a common point. So they're the same line. So L1 equals L2. I mean, you've got different looking parametric equations. Okay, but that's fine. They're still the same line. Unfortunately, you can't force any uniqueness on the parametric equations of the line. I guess that's why people like these symmetric. Well, no, that's not unique either. There's no uniqueness there. That's not unique either. I don't know why people like it. It baffles me. So that's how you would tell if lines are equal. First, check if they're parallel, and then see if there's a common point. If they were parallel but not equal, they would have no common points. Alrighty, so that was 250, 264, 268. All right, so point P and the normal vector, the normal or perpendicular vector to the plane, not the perpendicular vector to the plane, a perpendicular vector through the plane. The perpendicular vector through a plane is unique up to scalar multiplication because you can stretch it or smush it or flip it around or whatever, and it's still perpendicular. But other than that, it's unique. Okay, so find the equation of the plane with that point and that normal vector. Okay, so in order to do that, you need to we need to understand. Don't tell me they're doing 267. No, 268. I'm sorry. All right, so we have the point 3, 2, 2. Okay, so we'll draw a plane. And we've got this point here, 3, 2, 2, on the plane, and then we've got a normal vector to the plane. That's why the letter N is used, and that normal vector here is 2, 3, minus 1. So now, any other point on the plane, right? Any other point, x, y, z, on the plane, right? X, y, this vector here, x, y, z, minus 3, 2, 2, dot n is going to be equal to 0, always. They're perpendicular, because that's what the normal vector is. It's perpendicular to the plane. So any vector that's on the plane, is also perpendicular. So at this point over here, x, y, z, right there, that's perpendicular as well. So the vector x, y, z minus 3, 2, 2, well, so the point x, y, z, and then, you have this 0, 0, 0 here, and that's the vector x, y, z. You don't have to worry about that. So x, y, z minus 3, 2, 2 dot n is equal to 0. And that gives you all the points x, y, z on the plane. Every point on the plane satisfies this perpendicularity condition. And any point that satisfies that perpendicularity condition has got to be on the plane. Right, so that characterizes the plane completely. But it's not, let me write it this way. N dot x, y, or not equals 0 vector, 0 scalar. It's not typically written like this. Okay, I don't like to write it like that. I would rather distribute. So it's n dot x, y, z minus n dot 3, 2, 2 is 0, and then just move that guy over here. So n dot x, y, z is equal to n dot 3, 2, 2. Now that 3, 2, 2 is any point on the plane. Doesn't have to be the 3, 2, 2 if you had another point. Right? So this gives you a vector equation of the plane. Right, so now if we say like n is equal to capital A, B, well, let's do little a, b, c, little a, b, c, then you get the scalar equation of the plane. Is, well, it's ax plus by plus cz, that's this dot product, equals 3a plus 2b plus 2c. Right? And that will be your scalar equation of the plane. Right? So in this case here, in this one here, we have n is 2, 3, 1. So 2, 3, negative 1. 2, 3, negative 1, that's n dot x, y, z is equal to n 2, 3, minus 1 dot 3, 2, 2. Real simple. Real simple. Oops. So we've got 2x plus 3y minus z is equal to 6 plus 6 minus 2 is 10. So that's the scalar equation of the plane. Notice the scalar equation of the plane has the normal vector sitting there. Right? 2, 3, negative 1. It's just the coefficients of x, y, and z. The coefficients of x, y, and z, 2, 3, negative 1, that's the normal vector for the plane. And then, you know, this number here, if the number here is non-zero, that means that 0, 0, 0 is not on the plane. If 0, 0, 0 is on the plane, then this dot product is just going to be 0. Okay? But it's not in this case. So we know the plane does not go through the origin. Right. Notice n forms the coefficients of x, y, z. Of x, y, z in the equation, and 10 is not 0, so the plane doesn't go through the origin. Because if it did go through the origin, I could have used 0, 0, 0 here. It's any point on the plane. Okay, so that normal vector, it tells you almost everything about the plane. All right, and then two planes are parallel if their normal vectors are parallel, scalar multiples of each other. Two planes are perpendicular when their normal vectors are perpendicular. And the angle between two planes is just the angle between the normal vectors. Because the normal vector, right, is always just separated from the plane by 90 degrees. Right, so the angle between two planes is going to be the same as the angle between the normal vectors, just rotating that angle 90 degrees. It rotates the angle, but doesn't change the angle. All right. That was 268, 271, 272. So here's the plane. Find a normal vector. Express it however you want. Don't worry about unit vectors or coordinate vectors. Find the intersections of the plane with the axes, coordinate axes of coordinates, coordinate axes. Sketch the plane. Okay? So this is an important way of thinking about planes. So here in 271, what's the T mean? I forgot. Does it mean you're supposed to look at it somewhere? Anyway. So 4x plus 5y plus 10z minus 20 is 0. Okay, typically you put the 20 over here. So it's 4x plus 5y plus 10z equals 20. Okay, that's the plane. So the normal vector is what? It's the normal vector. It's just right there. coefficients of x, y, and z. It's 4, 5, 10. All right, so for the x-intercept, well, how are you going to find the x-intercept? How are you going to find the x-intercept?
Is it where the others are equal to 0?
Yeah. So you say y is equal to z is equal to 0. So now you got 4x is 20, so x is 5. Y-intercept, x and z are 0, so you have 5y is 20, so y is equal to 4. And then the z-intercept, x equals y is equal to 0, and then 10z is 20, so z is 2. So now this gives us a nice way of drawing. So the x, y, and z intercepts are positive numbers. So in that case, you can just do like this. So that's 5 on the x-axis. This is 4 on the y-axis. And then 2 on the z-axis. All right, so just draw that triangle. And that triangle is, it defines the plane. It's part of the plane, that triangle. It extends in, all the different directions. But it's a convenient way of just kind of representing the plane. I'm not even going to draw the rest of it. I'm just going to leave it as that. Right? So this triangle lives in that plane. It's the intersection of that plane with the first octant. The first octant where x, y, and z are positive. Right? The 3 coordinate planes divide 3-dimensional space into 8 regions called octants. Whereas in 2 dimensions you have quadrants from the x and y axes. Now here you have 8 octants. The first octant is where x, y, and z are all positive. And that's the intersection of the plane with the first octant. Right? So it's a nice way of looking at the plane. Something that you can draw that makes some sense. 272, same issue. It was 272, right? What I should do is So 272, 3x minus 2y, 3x plus 4y minus 12 is 0. All right, so this is 3x plus 4y equals 12. Right, so the normal vector in this case is 3, 4, and the coefficient of z is 0. Right, so x, y, and z intercept, well, it's not going to have a z-intercept, right? It's going to be parallel to the z-axis. Right, so because there's a 0 there, it means we're parallel to the z-axis. Right, the x-intercept, 3x is 12, so x is 4. The y-intercept, 4y is 12, so y is 3. So now when you want to draw this guy, right, so here's x equal to 4, y equal to 3. So that's the line down here, and then the plane just travels up parallel to the z-axis. I mean, why has it got to be parallel to the z-axis? I mean, there's not going to be a z-intercept. I mean, if I let x and y be equal to 0, Right? So z-intercept, none. If I let x and y equal 0, then I get 0 is equal to 12, which is obviously impossible, right? So there is no z-intercept. So the only way I'm going to avoid touching the z-axis is if I'm parallel to it. So that's that plane there. So 3x plus 4y equals 12. Uh, 281. So I like these kind of problems here. So we've got these 3 points given, P, Q, and R. And 3 points are enough to define a plane. So since 3 points are enough to define a plane, you have to be able to find the equation of that plane from 3 points. So P, Q, and R are given. Find the equation of the plane passing through P, Q, and R. And then, well, just find the equation of just part A. Forget about these B and C. Just find the equation of the plane. So I got 1, 1, 1, 2, 4, 3, minus 1, minus 2, minus 1. Okay, so nice little picture of our plane. So I've got minus 1, minus 2, minus 1. And then I've got 2, 4, 3. And then I've got 1, 1, 1. All right, so I've got this vector. And I've got this vector. And it doesn't matter, you know, which two vectors you're going to pick here. Just give them the same tail. Now, I don't have a normal vector. I need a point on the plane. I need a point on the plane and a normal vector. Well, I have 3 points on the plane. That's great. But I don't have a normal vector yet. So how am I going to get a normal vector? How am I going to get a normal vector? Well, a normal vector needs to be perpendicular to the plane. So it's perpendicular to every vector that's already in the plane. So what vector should I pick for the normal vector?
You cross U and V.
Yeah, the cross product of U and V. The cross product of U and V is perpendicular to both U and V, so it will be function as a normal vector for the plane. So the cross product, or any scalar multiple of the cross product that you like. So U cross V, or you know, some scalar multiple of that. So let's see. So 2 plus 1 is 3. 4 plus 2 is 6. 3 plus 1 is 4, so that's U. V is 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 1 is 2. Okay, so N going to be equal to that cross product I, J, K, 3, 6, 4, 2, 3, 2. So first, this 2 by 2 determinant. So 9 minus 12 is minus 3. And then this 2 by 2 determinant negated. So 6 minus 8 is minus 2. Negated is 2. And then, whoops, I did that wrong, didn't I? Now, the first one is this 2 by 2 determinant. So 12 minus 12, 0. And then this 2 by 2 determinant, 6 minus 8 is minus 2, negated. And then this 2 by 2 determinant, 9 minus 12, is minus 3. So that would be a normal vector. Right? So now the equation of the plane n dot x, y, z is equal to n dot any point on the plane that you want. Do 1, 1, 1. It doesn't matter which point you pick. The dot products are all going to be the same. Okay, so here we're going to have 2y minus 3z is equal to 2 minus 3 is minus 1. By the way, notice, so note, so n dot 1, 1, 1 is minus 1. N dot minus 1 minus 2 minus 1 is equal to what? So minus 2 times 4, sorry, minus 2 times 2 is minus 4, plus 3 is minus 1. And n dot, the last point, minus 1 minus 2 minus 1, oh, I just did that one, 2, 4, 3. Right, so that's going to be 243 dot n, so that's 8 minus 9 is minus 1. They're all the same. Right, so it's n dot x, y, z is equal to n dot a point on the plane. Which point on the plane? Whichever one you like. Doesn't matter, they're all the same, those dot products. Okay, pretty cool. Alrighty, so it's 281. 291. Determine whether the planes are parallel, orthogonal, or neither. If the planes are neither parallel nor orthogonal, find the angle between the two. And round to the nearest, round the degrees or whatever. So you have x plus y plus z is equal to 0. And 2x minus y plus z is equal to 0. So you have normal vector 1 is 1, 1, 1. Normal vector 2 is equal to 2, negative 1. Right? So n1 is not equal to k times n2. It's not a scalar multiple. Nor is the dot product 0. The dot product is 2 minus 1 plus 1 is 2, which is non-zero. So they're not parallel. Not parallel, not perpendicular. So the angle of intersection theta satisfies cosine of theta is equal to n1 dot n2 over n1 n2, so that same thing from before. So that's 2 over the length of n1, that's root 3, length of n2 is 4 root 6, so that's 2 over root 18. So, which is 3 root 2, that doesn't mean anything. So root 2 over 3, and that still doesn't mean anything. So theta is arc cosine root 2 over 3, which I did this one already, is 61.87 degrees. All right, so the picture in your mind is like that, right? You've got this plane, that plane. And the intersection of two planes is a line, obviously, if they intersect. So planes that are not parallel must intersect. And when they do intersect, they intersect in a line. So here's that line of intersection. And then this angle theta is in between them like that. Because that's the angle between their normal vectors, except with the normal vectors, you know, the angles are rotated. I'm not going to try to draw it, but the angle between the planes is going to be the same as the angle between their normal vectors, just rotated 90 degrees. Okay, so 61.87 degrees. So that's all the problems in section 2.5. So again, guys, you should be doing these problems on your own. You know, ideally before you come to class, but maybe you're not going to get all of them, and that's fine. Afterwards, you know, you should go over them again and make sure that you can do them. You can put pencil to paper and do these problems. Okay, because that's the problems that are going to be on the exam. All right. Let's take a 5-minute break and come back and do section 2. Hi guys. All right. So in section 2.6, I asked you to take a look at, problems number, where are they? Oops, what did I do? Ugh. Problems number here. Okay, for the following exercises, rewrite the given equation of the quadratic surface in the standard form and identify the surface. More so, what I wanted you to do is just to draw the surface, sketch the surface. And this is what I'm going to be asking you about on the exam. Okay, so the way I explained it is to look at the cross-sectional area in cross-sectional sketch traces of the surface. So level curves or traces or different things that you might call them, and find where the circles or ellipses are. Okay, in which parallel to which coordinate plane. Okay, well, so here in number 319, minus x squared plus 36y and z squared equals 9. All right, so if I look at the cross-sectional slices of the surface, okay, that are parallel to the YZ plane. Okay, so parallel to the YZ plane. So if I make, say, x a constant, or if I make x equal to 0, let's let x equals 0. Okay, or let x equal any constant. First, let's let x equal to 0. If we let x equal to 0, what do we have? We have 36y squared plus 36z squared equals 9. Okay, these are circles. All right, I don't care how big the circle is or if it's an ellipse. So here's the y and z axes, and I've got a circle. So more generally, for x equal to k, right? Just x being equal to any constant, then I have 36y squared plus 36z squared equals 9 plus x squared, k squared, sorry. Okay, this is a constant. So again, you're going to have a circle. So in the planes in XYZ space that are parallel to the YZ plane, we have circles. So you have circles like perpendicular to the x-axis. So circles parallel to the YZ plane, or perpendicular to the x-axis. So now, in order to draw it, all I need to know is what does the silhouette of those circles look like. All right, so for the silhouette of those circles, you'll zero out some other coordinate. You'll zero out the y and zero out the z. So if I let y equals 0, what do I get? I get minus x squared plus 36z squared equals 9. All right, let's divide by 9. Okay, so this gives me minus x squared over 9 plus z squared over 9 over 36. 9 over 36 is what? Divided by 3. Well, it's 1 over 4. Like that. Equals 1. So now, what is this? I mean, don't think too much about what those numbers are, but what kind of curve is that? In the XZ plane. Right. Remember the form of the hyperbola. Okay, a hyperbola has a basic equation that looks like this. X squared over a squared minus y squared over b squared equals 1. And then the graph of the hyperbola looks like this. All right, so on the x-axis, you look at the a and the minus a. And on the y-axis, you look at the b and the minus b. And then you've got this box, this rectangle, going through those points. And then the diagonals of that rectangle, they give you this sort of guide for the slant asymptotes of the hyperbola. Now, which way does the hyperbola open? It opens along the positive one, the positive variable. So the axis for the positive variable. So this is positive x squared over a squared minus y squared over b squared. So it opens up this way. So it looks like that. All right, that is that's the basic equation for the hyperbola. And that's what we've got here, right? We got x minus x squared over 9 plus z squared over 1/4. Okay, so we've got hyperbola in the xz plane opening up along the z-axis. All right, and then if you let z equal to 0, you get the same thing. You get minus x squared plus 36y squared equals 9. So minus x squared over 9 plus y squared over 1/4 is 1. All right, so again, hyperbolas in those planes. So now that allows me to draw this surface, this quadratic surface, and it's going to be a hyperboloid of one sheet. So x, y, z. So the circles or ellipses are parallel to the YZ plane. And then I've got these hyperbolas opening up along the y-axis and the z-axis. So let's see. Hyperbola in the xy plane opening up along the y-axis, just something like that. Okay, and now we draw the circles that follow it. Okay, it gives you a pretty good look at what that surface is like. All right, a pretty good look at what that surface is like. Now, remember and it doesn't matter if these cross sections are circles or ellipses, because when you turn a circle, when you tilt it sideways, what does it look like, right? I mean, when you look at a circle head on, and if you tilt it in whatever direction, it becomes elliptical looking. Right? If I tilted it along this vertical axis, then what I see is an ellipse. Right, the front looks a little bigger, and the back looks a little smaller, further away. So it turns elliptical, or like an oval or something like that. So it doesn't matter if it's a circle or ellipse, because when you slant the thing, it's always going to be an oval sort of shape. All right, so that's 319. 321. So minus 3x squared plus 5y squared minus z squared equals 10. Okay, what variable, okay, do I have to make a constant? When I make it a constant, the leftover variables will define an ellipse or a circle. Right? And remember, an ellipse has an equation that looks like this. Right, that's A, B, minus B. That's a terrible picture, but try it again. Still bad. Okay, passable. All right, so here, which variable should I make a constant? Right, we're going to make the y a constant. Y equal to k. Because if I let y equal to k, I get 5k squared minus 10 is equal to 3x squared plus z squared. Right, now, of course, this number over here needs to be positive, but that just depends on what k is. So I have ellipses. Right, this 3x squared plus y squared. The point is that this is positive and that's positive. Plus something times x squared plus something times y squared equals 1. Right? So, I mean, of course, I have to divide out by the 5k squared minus 10 or whatever to get it into this form, but that's not important. Right? Both of the terms here are positive. If one term is negative, then you get hyperbolas. If two terms are negative, again, you'll get ellipses, right? Just by switching the sides of the equation. All right, so I have ellipses parallel to the xz plane. Okay, don't get hung up on what that ellipse looks like. It's just, it's just something elliptical. And it's parallel to the XZ plane. So now the question is, what does the silhouettes of the ellipses, of the different ellipses look like? So you zero out some other variable. We'll zero out the x, say. So if we let x equal 0, all right, then I have 5y squared minus z squared equals 0. And so you get, in the yz plane, hyperbolas opening this way on the z-axis. And then if you let, that's x equals 0, if you let y equals 0, if you let z equals 0, then you get minus 3x squared plus 5y squared equals 0. So again, you get hyperbolas in the xy plane opening up along the y-axis. So now let's put that idea in three-dimensional space. Actually, you didn't need to check this second one. Just zeroing out one of the variables is enough. But we'll just do 2. So the sketch of the surface looks like this. So here are the ellipses in the YZ plane. So that's the y-axis. And that's the negative y-axis. And then I also have over here in the xy plane, but I'm not going to draw that. And then we're going to have, these don't look the same at all, do they? Circles parallel to the YZ plane. So they look like this. So that's parallel to the YZ plane. And notice there's like a gap in there. So this is known as a hyperboloid of 2 sheets. I didn't put that in the right spot. Kind of look like Captain America's shield. Okay. So it's not that difficult, all right? Like, we need to be able to draw a few of these things, visualize a few of these surfaces, because all the examples really that we're going to go over later, these surfaces are used in those examples. So we need to understand the shapes of these things. So let's try another one. Let's see.
Dr. Salati, I don't think you started recording again, did you? Oh, no, you
Oh,
sorry.
I did not, did I? Oh, no, I did. That's good.
Oh, sorry. I'm used to it being on the collaborator.
Thank you for being on top of that. Well, it would have been a problem if I didn't. Since we don't have the full class here. So let's take a look at 329, a little bit different. So in 329, 6x plus 3y squared, 6x equals 3y squared plus 7z squared. Right, so if we let x equal to k, then we have 6k is equal to 3y squared plus 7 z squared. So we have ellipses parallel to the YZ plane again. And then let's just look at, let's make z equal to 0, y equal to 0. Well, let's make them both equal to 0. So if we let y equal to 0, we have 6x is 7z squared, right? Or x is equal to 7/6 z squared. And what's that? That's just a parabola. Right? So in the xz plane, I've just got this parabola. And if we let z equal so if we let z equal to 0, same thing. We have 6x is 3y squared. Right? So x is equal to a half y squared. So in the yx or yz plane, I've also got parabolas. Or wait a minute. In the xy plane. In the xy plane. Oops, not this way. This way. Right? In the xy plane, I also have a parabola. So ellipses parallel to the yz plane framed by a parabola. So this gives me this paraboloid picture. So there's a parabola opening up along the x-axis like that. Don't need to draw really that other parabola. This is enough to sort of frame that. So we see these ellipses parallel to the yz plane, and then we have these parabolas just sort of framing those ellipses to turn it into, you know, a nice smooth surface. Okay, so take a look at the rest of the problems that I assigned in this section. So 319 through 329 here are odd. You know, and sketch those surfaces. Find the ellipses and parallel to which plane, and then find the curves that frame them, and then you'll be able to draw the surface. All right? If you need any extra help, you know, just let me know, and we can find a time and meet. I'm going to announce, by the way, by email. I'm going to start having some regular office hours, I think. Do you guys, so if I'm going to hold regular office hours, do you guys want me to hold it on Monday, Wednesday? Or do you guys want me to hold it on Tuesdays and Thursdays? What do you think? What's your...
Monday, Wednesday works better for me.
I mean, like, you know, on the same day as class or not the same day as class, essentially. Or, you know, I could do one of each. I could do one of each. I'll do like Tuesday, Wednesday or something. Monday, Wednesday. Does anybody want Tuesday, Thursday? I think Monday, Wednesday makes more sense. Because you guys are sort of in, you know, thinking of the material maybe at this point. If you can't make it to the scheduled office hours, you know, just email me. We'll set up a different time. I should have some regularly scheduled office hours, and I'll give you a link to where to go. Use WebEx or something. Alrighty. So moving on to section 2.7. Cylindrical and spherical coordinates. So 363. Did I know? Yes, should put section 2.6 here. So 363. So this is the picture. Well, use the following figure as an aid in identifying the relationship between rectangular, spherical, and oh, they're trying to do all of them in one picture. I'm not quite like too keen on that. Anyway, so 363, for the following exercises, the cylindrical coordinates r, theta, z are given. Find the rectangular coordinates x, y, z. So the r, theta, z, the r and theta are just polar coordinates. So polar coordinates in the xy plane. So instead of x and y, we have r and theta. Same polar coordinates as you were looking at in Calc 2 and other classes you might have had. And then z is just z. So 4 pi over 6, 3. All right, so again, the cylindrical coordinates. Okay, so this is the point r theta, and then you just put a 0 for z. And then if this length here is z, then this is the point r theta z. So it's just polar coordinates extended to 3 dimensions along a perpendicular line, the z-axis in this case. So x is r cosine theta, y is r sine theta, same stuff as before. X squared plus y squared is r squared, and z is just z. There's no transformation there. So here x is 4 cosine pi over 6. Y is 4 sine pi over 6, and z is 3. So this is 4 times root 3 over 2, and this is 4 times a half, and that's 3. So x, y, z is equal to 2 root 3, 2, 3. So we go from r theta z to x, y, z in the same way that we did before with calculus 2 in polar coordinates. Okay, so 367, now spherical coordinate, wait a minute, the following, given x, y, z, find r theta z. So 367, given x, y, z equal to 1 root 3, 2. Okay, find r theta z. Okay, well, x is r cosine theta, y is r sine theta. So then y over x is tangent theta. So you find the theta that way. All right? Y over x is tangent theta. So y is root 3 is equal to tangent theta. Right? And theta is in the first quadrant because x and y are positive. In quadrant 1. Right? So so theta is arctangent of root 3. Right? Is root 3 over 2 over 1/2. Right? So root 3 is root 3 over 2 over 1/2. So they're using those special angles, although there's no real reason to be using them. So that's the sine over the cosine. So this is theta equal to 60 degrees, which is pi over 3. Right, so theta is pi over 3. Right, and then how would you find r? Right, so x, right, x is r cosine theta. So x is equal to r cosine theta. Oh, sorry, well, r squared is x squared plus, this is the easier way to do it. Right, r squared is equal to x squared plus y squared is going to be 1 plus 3 is 4. So r is equal to 2. Right, so r theta z is equal to 2 pi over 3, and z is just z. It's just 2. So there's your answer there. Right, so the only issue here in going from xyz to r theta z is finding theta. Right, so theta is arctangent of y over x, and then you have to figure out what quadrant you're in. If you're in quadrant 1 or quadrant 2, you know, then you can just take the arctangent off the calculator. If not, then you have to take the arctangent and add 1 and add pi to get it into quadrant 3 or quadrant 4. All right, 367. $371. So find the equation of the surface in rectangular coordinates and identify the graph of the surface. Okay, so what you can do is you can take the surface, the equation for r, theta, and z, and transform it into x's and y's. And then maybe you recognize the surface, or you know, you could just recognize the surface from the equation. So in 371, we just have r equal to 4. Right, which is the same as saying r squared is 16 and r squared is x squared plus y squared equals 16. Now remember, given the equation for x, y, and z, if one of the variables doesn't appear, then you take the two-dimensional curve that's generated by the equation and then extend it along the axis of the missing variable. Right, so x squared plus y squared equals 16. That's just the circle of radius 4, right? R equals 4 in the xy plane. Right, so you take that circle in the xy plane of radius 4 and you just extend it along the z-axis. Because z can be anything. X and y are constrained in this circular fashion or whatever. So, but z can be whatever you want. So you just get copies of these circles for every different value of z on the z-axis. Right, so you get the circular cylinder moving along the z-axis, parallel to the z-axis. So r equal to 4, that's what you get. You didn't have to transform it here into rectangular coordinates, but we did. So this 371, 372, z equals r squared cosine squared theta. Right, so this is just z equals r cosine of theta squared, right? So but r cosine theta is just, you know, is just x. So you just have z equals x squared. So in the xz plane, you've got this parabola. And then you just extend that parabola. Oops, I'm not doing it right. In the xz plane, you have this parabola. And then you just extend that along the y-axis, right? We have y missing in this equation here. Y is missing. So I'm just going to copy, I mean, I know you can't do this unless you've got an electronic thing that you're drawing with, but just to give you the idea of how to do it. It's hard to draw on this thing because the surface of it is slippery. So the stylus, it just slips. So what you do is you just take copies of that guy and move it along, extend it along the y-axis. Then you can just link them up with straight lines parallel to the y-axis, and there it is. So it's this parabolic sheet, or often called a parabolic cylinder, if you will. Anyone ever been to the desert out in California, Barstow, California? If you ever do, they've got these solar power plants. They don't use panels like photovoltaics. They have these mirrors, and the mirrors are these parabolic sheets. So there's these parabolic mirrors, and like at the focal point of the mirror, right? Because a parabola has a focal point. So I mean, if the light's rays are all coming in like that, parallel, then they all just bounce off the mirror and come to this focal point in the middle. In that focal point, there's like a pipe with oil, some kind of oil or whatever going through it, and that gets heated up, and then you just spin the turbine with that heated oil. It's kind of cool. It's really ingenious. So that's 372. $375. Well, actually, we are out of time. So this is just R equals 2 cosine. Oh, let me show you how that goes real quick. So 375. That's a good one. So R equals 2 cosine theta. So multiply both sides by R. So R squared is x squared plus y squared, and then this is 2x. All right, so that's a sort of non-obvious transformation, I guess. So you get x squared minus 2x plus y squared equals 0. So then you complete the square. Plus 1 plus y squared equals 0. So that's x minus 1 squared plus y squared equals 0. So that's a circle in the xy plane centered at 1 comma 0. So it's the it's that cylinder again, but it's not centered on the z-axis anymore. It's just parallel to the z-axis. Actually, it runs along the z-axis. So that's the z-axis right there. And here is the x-axis. This is 2, and this is 1. And then the y-axis is here. So it's x, y, z. So that's the point 0 or 1, 0, 0, because that's the circle centered at 1, 0 in the xy plane. So then that just gets extended along the z-axis there. But that's a cool transformation how that worked. I didn't square both sides, by the way. I multiplied both sides by r. Multiply both sides by r so that the cosine theta becomes r cosine theta. Okay. Alrighty, so that's all for today. So I'll post everything onto the website and on YouTube. And for Wednesday, we're going to need to look at the video lecture for 3.1 and 3.2. Okay, so go to the video lecture for sections 3.1 and 3.2. Okay, all right, have a good night, and I will see you on Wednesday.